Yeah, chapter 17. Where is that button? Right here. Okay, so let me make sure I am recording. I can tell that by this right here. Yep. And then you can hear my voice and I'm sharing. I try to do a 3-point check now. Okay, so this chapter here picks up where we left off from chapter 16, talking about acids and bases. In chapter 16, we saw that the acid essentially has two general forms, right? In the acid molecule, you have a hydrogen and a nonmetal for the binary acid, and then you have a hydrogen, oxygen, and a nonmetal for the oxy acid, right? For the base, the general base was, let's see, metal hydroxide. We talked about strong acids and weak acids, right? So these are both acids right here. This is a base. And so I want to give the list real quick, a list of examples of strong acids. So with the strong acids, in the previous chapter, we talked about the following strong acids. Okay, and the way I remember the strong acids is I look at group 7, the periodic table, and I have my periodic table right here. So group 7, I started with fluorine, chlorine, bromine, iodine, right? And then AT. So I'm going to show you the ones that I leave out. We don't really learn about AT, astatine. Okay, and somebody asked me one time, why don't we learn about that? Sometimes stuff is left out because chemists understand and they do have compassion that the information is overwhelming. If astatine is not commonly used in the lab, why really learn about it, right? If it's too expensive or it's hard to acquire, whatever, you just apply everything else you learn to it, even though we don't actually exclusively learn about it. So for our strong acids, I will actually take fluorine away from here. Okay, and that will be the list of strong acids. Hold on a second, right here. I'll put fluorine here. So for a strong acid, the first three are add an H to Cl, add an H to Br, add an H to I. These are 3 of the 6 strong acids. So these make the binary portion, right? And you can see why they're binary. They're binary because binary usually stands for 2. You have a hydrogen and the other nonmetal, hydrogen, the other nonmetal, hydrogen, the other nonmetal. And then for your 3 remaining strong acids, so remember there are 6 strong acids total. These are the first 3, 1, 2, 3. Let me write it that way. For the 3 remaining oxy acids, which are strong acids, we have these common ones, H2SO4. You can see it's oxy because you have more than 2 elements. You have hydrogen, sulfur, oxygen. You also have nitric acid. These are common acids that we use. And then we have perchloric acid. So this is 4, 5, 6. That. Okay? And these are your oxy acids. So you want to make sure you memorize these 6 strong acids. It helps you a lot. Memorize them in 1412. Don't wait till organic chemistry to go back and say, oh no, she said, right? She said we should memorize it. I forgot to memorize. There's a very, 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 very long list of acids. Only these 6 acids are strong. The rest of them are weak. So for me, as a person who naturally struggles with just straight up memorizing things, I memorize the 6 strong ones. So any other compound that I recognize to be an acid was automatically weak. Okay, so that's a longer list than this list right here. For my weak acids, though, I'm not going to go over the long list because there's a lot of them. I'm going to go over the common ones that are covered in 1412. Okay, so remember how F, fluorine, in group 7 didn't make it in the list? F is actually a weak acid. So this is the first weak acid. What's another common weak acid we talk about? NH4. Let me just stick with the compounds. Oh, acetic acid. Acetic acid. Acetic acid, let me write this the general chemistry way. Give me a second. The organic way is CH3COOH. The general chemistry way is H C2H3O2. There. Okay. Organic chemistry, they write it this way because remember, organic chemistry, the focus is carbon. So even when they write the acid, the carbon element is the one that precedes in the formula. In general chemistry, things are more seen more in the generic view. So they write acids in the format where H is the leading element. So it's the same formula, it's just written differently. Here, general chemistry, the leading element is the H for the acid. Organic chemistry, the trailing element, the last element is the acidic hydrogen. Okay, while we're looking at this, I want to mention something real quick. No, just because a compound has a hydrogen doesn't mean all the hydrogens can be lost. Okay, so I want to make sure I write this down. Just because a compound has hydrogen atoms does not mean that all the atoms can be, let me add a page here, released in solution. Okay, I feel like I could have said that better, but the point being that just because the hydrogen is in the formula doesn't mean that all the hydrogens can be released in the solution or lost to the solution. So our example here is acetic acid. So I'm going to write this down here because somebody asked me this question one time. HC2H3O2. This is acetic acid, also known as vinegar, right? Acetic acid. 1411, we learn how to name this. This is the acetate ion. So somebody asked me, why do we say when this compound breaks apart, it breaks apart to release only one hydrogen? So we'll be talking about this in a little bit. This is a weak acid. So when it breaks apart, I'll just do it without water so y'all can see. When it breaks apart here, why do we show that only one hydrogen ion is released and the rest is C2H3O2 minus? Why do all four hydrogens, why are these three here not released? Because the position of this hydrogen ion when you draw the structure allows it to be easily released. These hydrogens here are attached to carbons that make it harder. And not only carbons, their position makes it harder to release. So these are called non-ionizable hydrogens, while this one here, based on its position, is ionizable. Ionizable means can be broken off from the compound to make an ion. Okay, so when we're actually working on this, please notice when I'm actually writing out my equilibrium reaction and everything, even though this compound has got 4 total hydrogens, I will always be releasing only one for this acetic acid. And then when we start writing our Bronsted-Lowry reactions, right? Bronsted and Lowry equilibrium reactions, please note I will take the weak acid, HC2H3O2, add this to water, like you guys saw before, because there's a format, a trend, the way it happens all the time. The weak acid will be aqueous. The water will have to be in liquid state. And then, since I said it's an equilibrium, I have to have my equilibrium arrow. And since I said this is, well, it's equilibrium, but it's equilibrium of an acid, our focus here is acid equilibrium. One of my products has to be H3O plus. So the H that got released here combines with the water to form H3O plus, aqueous. And then this other ion remains here, C2H3O O2 minus. This is also aqueous. Remember, we put the subscript aqueous for ions that are in water. So ion because you have the charge, and this is in water. So this right here will be my equilibrium reaction for acetic acid or weak acid. Okay. Okay, now I've done a quick recap. Let's go ahead and start this chapter. This chapter is called aqueous ionic equilibrium. So we're moving on from what we covered in the last chapter. It talks about buffer solutions. So we're going straight into that. What exactly is a buffer solution, right? When we say buffer solution, what does this mean? It says here, these are solutions that resist changes in pH when an acid or a base is added to the solution. If you've taken biology class, you have learned about a buffer. We have a basic, slightly basic buffer in our blood. It's a sodium bicarbonate basic buffer that keeps our blood pH around 7.4. Blood pH at approximately 7.4. So our blood is slightly basic. Okay. So a solution called a buffer is a solution that's able to resist pH, or you can say maintain a constant pH. So it resists pH changes or maintain a constant pH when two types of chemicals are added. The chemicals are either an acid or a base. If the chemical added to the buffer solution is not an acid or a base, the buffer cannot resist it. The buffer is only equipped chemically to to counteract the effect of an acid or a base. So think about this. Ooh, okay. In a military term, okay, like I'm going to walk cautiously, right? The threat here to the solution is the acid or the base, but the buffer is only equipped to deal with acid or base threats. If the threat is anything outside of acid or base, the buffer cannot resist it. Okay. So we're told here the components of the buffer. How do they act? These are chemicals. How do you neutralize an intruder or neutralize the enemy? It says here the buffer acts by neutralizing, literally, not figuratively, neutralizing the acid or the base that is added to the buffer solution. So quick recap on neutralization. We covered this in the last chapter, right? Wait, where am I right now? Slide 4. We talked about this in chapter 16. Neutralization reaction. Neutralization happens when acids and bases react. So it's important to know this terminology so when you're reading through it, you understand what's being communicated. Neutralization happens when an acid reacts with a base to form salt and water. And I told you before, neutralization, the context here is pH. And neutralize means to make pH neutral. I also mentioned before that these, both salt and water, they usually have a neutral pH, meaning pH of 7. So for the most part, acids have low pH, bases have high pH. When I say low pH, I mean less than 7. How do I write this? pH is less than 7, right? And when I say base has a high pH, the pH is greater than 7. But when you react these two, you make two products that usually form a neutral pH. Now, this is not true all the time, but this is usually the normal, okay? So this is how they act. Buffer solution must contain either. So this is the ingredients, right? Not the step-by-step ingredient, but kind of the gist of it. You must have significant. And this word significant here is very important. For the chemical to neutralize and to neutralize for a long time, there must be enough chemical. So when they say significant here, another word I would like to use that may have more punch is large, lots and lots, large amounts of weak acid and its conjugate base, or large amounts of weak base and its conjugate acid. Okay? Because remember, what's happening here is a chemical acting as a defense system to a solution. This chemical is added with that goal in mind. The chemical will neutralize any incoming acid, see it as a threat, neutralize it chemically, as we saw before here. If it's the base, it will do the same thing. But if you want to have a defense system for a long time, you have to have the chemical present for a long time. How do you accomplish that? Have large amounts of it. Okay. What is the chemicals we're using though? They're telling you here. You're going to use a weak acid and its conjugate base, a weak base and its conjugate acid. So, once again, I'm decoding what they're writing, right? So, weak acid. Since I just used acetic acid as a weak acid, I'm going to use that. Let me say I pick acetic acid, HC2H3O2. This is going to be my weak acid, right? I already defined the list. Weak acid is that. And I need its conjugate base. So remember we talked about acid, conjugate base. So if this is my weak acid, my conjugate base that is going to match that weak acid conjugate base will just be the ion minus the hydrogen ion. So the anion. This will be the ion of a conjugate base. Okay? So the weak acid and its conjugate base. Remember, the conjugate is always what gets left behind once the proton is removed. We discussed this in chapter 16. So here's the thing. We're talking about these two together in large amounts mixed together, providing the buffer. Now let's talk about what's happening in real life. Say, fast forward years later, you're working a job where you have to make a buffer. And then you realize, oh, I'm trying to make a acetic acid buffer, a weak acid buffer. I don't have the conjugate base. I want to buy it. So I'm going to call Sigma Aldrich, a company that produces chemicals, and I want to buy the conjugate base. You can't find ions like this freely floating in the universe. You can't find them in containers. When you buy stuff from the store, it usually comes in elemental form or in a compound form with neutral charge. So what I'm trying to say here is the conjugate base, even though this is a desired chemical, you will usually get it with a counter ion. So this will be in this form. It can be sold to you as sodium acetate or potassium acetate or any counter ion. And sometimes it's written like this, or the sodium is at the end. Either way, okay? So I need to bring back solubility for 1411. Why is it okay to buy this when your goal is to get this? Here's the thing. All sodium compounds are soluble in water. Once you take this compound here and put it in water, the sodium acetate will break apart and give you your desired ion. This in water will completely break apart and it will release the sodium ion. You don't want this, but it will give you the ion you want. Okay? So I'm letting you know this now because even though they define the buffer as this and this, all of a sudden they start using this chemical. And if you didn't see the switch, you were like, wait, sodium? What is sodium doing here? Right? Sodium is just that counter ion, the escort ion that makes it possible for you to get access to this. We don't care much for this. We just care about the ion we want.
Now, if the element was supposed to be in there, and let's say, for example, the C2H3O2, if you would put that in water, would that like dissolve it and make it weaker? Or is the sodium like balancing it out to get the full C2H3O2? Is that what it's doing?
Wait, you're saying, so here's the thing. You can't get access to this without the sodium. So there isn't a scenario where it's possible for you to just get access to this without the sodium. In nature, ions want to combine with something else. So the chances of you just getting this by itself without the sodium are slim to none. But once this gets in water, it will just dissolve in water and stay in water in this form. It won't break apart. So I don't know if I've really answered your question.
Yeah, you did. Thank you.
Okay, right. So there's a bond between sodium and the rest of the ion, but once this part here gets in water, it remains as a unit. And then this is the one that then interacts with the other one. So that's the first thing. The other thing I want to mention, I, I know the reason why I said the slides were a lot longer than it seemed because there's a lot of backstory they don't tell you. And if you're reading through and you don't get the backstory, you get a little lost, right? I just said you take an acid and add it to a base to make a buffer, right? Didn't I also say down here that acids and bases, or I guess it'd be up here, acids and bases react to neutralize each other? Because that's the kind of question I will ask. Like when I really listen. Like I know I need to listen. That I will say, don't acids and bases react with each other? When you take an acid and the base, they're gonna react to form salt and water. Okay, so this makes me a slow listener and a slow reader because I need to process everything I'm reading. So let's try to react this acid with the base. HC2H3O2 plus its conjugate base, C2H3O2. So let's pretend they react. The only way they can react is with this H combining with that. And what does it form? HC2H3O2. And then this one will be left by itself, which would be C2H3O2. Do you see what they just did? They deliberately picked an acid and a base where they can't really combine with each other. Even if they mistakenly combine with each other, they just remake each other. The reactants here literally match the products. So the combination in making a buffer is such that you don't, when the acid and base get together, the initial goal is that you don't want them to attract each other and react with each other, even though you know that acids and base tend to react with each other. So you pick a combination such that even if they happen to react with each other, they will reform each other. So you still have your ingredients that are going to neutralize the acid and the base. Okay. So that's the other thing here. Other than that, we'll continue from here. So to make a buffer, weak acid and conjugate base. The other thing I'm looking at here is to set a basic buffer, right? So what you guys saw in chapter 16, I mentioned, oh, I forgot to mention weak base earlier. For your weak base, the most common one, oh, real quick. Yeah, for your weak base, the common one is NH3, ammonia. Yeah, ammonia. Ammonia gas, ammonia solution, whatever, ammonia. This is your most common base. So you have ammonia base or ammonia organic bases. So this is like NH3 or organic compounds like CH3, NH2. So bases that have nitrogen in them. These are common weak bases. So when you're aware of these, you're doing good. Okay. So I'm going to pick this one here. This is the most common base in 1412, NH3. So if you're dealing with a weak base and its conjugate acid, we're going to make a basic buffer. In the case of a basic buffer, the combination you have to use here is a weak base. So I'm going to use NH3 and the conjugate acid of the weak base, the conjugate acid. Now, I explained last time in chapter 16, to go from a weak base to the resultant acid, you have to add H plus. So take this formula here, add H plus, we get NH4 positive, right? Like I explained before, you cannot go to the store and find a compound that has an ion, or sorry, a polyatomic ion. You cannot call the store and say, can I get ammonium ion? You have to say the compound. So if you're trying to buy this in the store, right, this will usually come in the form of maybe ammonium chloride. where chloride is the counter ion that when it gets in water, chloride will break off to reveal the ion you want. So somebody told me chloride is an escort, kind of like a prom date, right? If you are going to the prom, your date is just escorting you there, but the important person, the important player in the story is you, right? So in this case, the chloride ion is just the escort, the accompaniment to ammonium ion. When it gets in water, it separates. I know another person told me in class, like the father of the bride. I'm like, that's a better illustration. I keep forgetting that one. When the bride is walking down the aisle, the father is just walking her down the aisle. It's just tradition, right? But when she gets to the front, he walks away from her, and then she's the one who continues getting married. So I guess this is a better. I have to remember that one first. The chloride here is like the father of the bride, the counter ion. Helps us to bring in ammonia in the solution, and then when it gets in the solution, it breaks off and it doesn't have an important role anymore, right? So yeah, so just like we had sodium here and lithium being the fathers of the bride for this ion here, the escort ions, now we have chloride, okay? So these combinations together can also make a buffer. And we'll see this play out in a lot of words later on down the slide, but I want to show it to you in a simplified version. So when we get to that, I can just kind of review over it, okay? So they give you an example like I gave you earlier. Example of a buffer system. Blood has a mixture of a carbonic, a weak acid buffer. So they're telling you blood has a mixture of a buffer, which is H2CO3 and HCO3. The buffer combinations, if you look at them, there's usually like it's off by H plus, right? So from here to here, there was an H plus that was lost. So this is a conjugate base pair system, right? Conjugate acid and base pair system, right? So now let's go ahead and move on down here. You will see what I talked about shown again. Now we're making an acidic buffer. We're told an acidic buffer solution must contain significant, once again, large amounts of both the weak acid and its conjugate base. Usually the conjugate base is added to the solution as a salt. You see how I already told you that, right? I told you all this. When you have the metal in there, this is actually a salt. So sodium acid is the source of the conjugate base. So hopefully now you're seeing this is a review of what I stated. The sodium ion is just the escort, the father of the bride, so to say, is escorting the acetate ion into the solution. Once it gets into the solution, it separates. So here we have the conjugate base. It was in the form of NaC2H3O2. But once it gets in solution, these separate. So the story continues with C2H3O2 minus. The weak acid HC2H3O2 remains like that. So you mix large amounts of both to make your buffer. So they're showing you here when the solution gets made, this is the mixture, right? They're not reacting with each other, so they call the solution. This is the formula of the base. And this is the formula of the weak acid. So I should actually call this the conjugate base because it's not just any base. They hand-pick that base on purpose so it doesn't react with the acid. So this is the conjugate base. And so you can see them here. This is our buffer. When everything is playing out, this is our weak acid that we added. This is the conjugate base. I'll call it CB for conjugate base. Okay? And you have the hydronium ion. So we'll talk about the hydronium ion in a moment here. Okay. So here they're showing you play by play what is happening to make the buffer. Because remember back here they said we are making an acidic buffer solution. So in this next slide here is showing you play by play what happens. An acidic buffer solution. So for this part here to make sense, I would say we're still making the buffer, but in the process, we're talking about how the buffer will work and why we're picking the ingredients we're picking. Imagine the container has the weak acid first. And to this, you are about to add uh, the conjugate base. Okay, so first you have the weak acid first in the container. You are about to add the conjugate base because your goal is to make a buffer. This is your goal, make a buffer. So, and the reason why I'm saying that you're starting with a weak acid first, because look at our equilibrium we have here. We have an equilibrium of a weak acid. How do I know that? This is a weak acid, this is water, and these are being reacted to form the products, acetate ion, H3O plus. H3O plus shows you this is a weak acid equilibrium like I showed earlier, okay? So the total here, buffers work by applying Le Chatelier's principle to the weak acid when you're trying to make it. If a strong base is added to the buffer solution, the added base is neutralized by the weak acid component in the buffer. Okay? So they're showing you here how the buffer will work. Okay? So let me go ahead and write this on another page as I illustrate this a little bit better, or at least I try to illustrate this a little better. I think it's a little better when I rewrite it from scratch. So I'll start with this equilibrium here. I have my weak acid, obviously, and then I have my water here for my weak acid equilibrium. And then over here, I have my conjugate base, C2H3O2 minus AQ plus H3O plus AQ. So you see how the H that was lost here went to the H2O, so that's how we have this here. Okay, so I'm gonna label the chemicals that are gonna be neutralizing. So we started off right here, right, with the weak acid being in the container. And then we added the conjugate base. So the conjugate base actually adds to this part right here, right? It adds to this part right here. And we'll see how that plays out. This is a conjugate base. It adds to this part right here. So it's actually going to do something to alter the pH of this equilibrium. So we'll go into all that part, how adding to the conjugate actually shifts the equilibrium left. I'll go into all that part when I get to the slide that has the picture of the beakers right here. Okay? But before I get into that, we're looking at the general role of each component. Once the buffer is made, after I've added the second component, let me erase this part here. Let me highlight the role of this each component. The role of the weak acid, once the buffer is made, will be to neutralize any added base. So this is the part I'm talking about right here. The weak acid in the buffer will neutralize any added acid. Oh, sorry, any added base, my bad. I had to look over it again. Any added base, right? So the acid will neutralize any added base. Once you have your buffer ready, you got everything mixed up. You've had the weak acid conjugate base in there. How are they reacting? How are they acting? You have your weak acid neutralizing any added base. So it's important in your recipe to have the weak acid because the weak acid will neutralize any added base. Okay? Why is it important to have the conjugate base? The conjugate base also has a role. What's the role of the conjugate base? The conjugate base right here, this will neutralize any added acids. So I'm going to write this down here. The conjugate base in the buffer will neutralize any added acid. Because remember, neutralization is a kind of reaction happening between an acid and base, right? So the conjugate base disarms the acid by reacting with it, kind of like self-sacrifice. Okay, so this component will sacrifice itself anytime the threat that's added is an acid, and then this component here will sacrifice itself anytime the threat added is a base. So this will react with base, this will react with acid. Oh, I should say react with, not react with, it's implied with acid. Okay, and that's how the buffer works. That's like the oversimplified version. Weak acid reacts with base, conjugate base reacts with acid, and so the acid and the base that are kept in check, they're neutralized, they're disarmed. Okay? So here they're showing you how it happens play by play. So I showed you the simplified version. Now we can see what they're saying in words. They're saying here, buffers work by applying Le Chatelier's principle to the weak acid equilibrium. If a strong base is added to the buffer solution, it's a base, strong base. Then if it's a base, this part has to react, right? That was the role of the acid, of even having that weak acid. The added base is neutralized by the weak acid component, this part here, like I just said, in the buffer. So this is showing you how it plays out, how we are neutralizing it. This is the strong base that got added. This is our weak acid here from the buffer. The weak acid is using itself, right? The chemical has to react. So it's neutralizing the added base. So all the weak acid doesn't react. Some of it reacts, some of it still remains, right? That's why you have to add a lot of it. And then it neutralizes the base and makes some water, which is of zero consequence, and salt. But wait, doesn't this salt look familiar? Yeah, this salt is the same salt that made the conjugate base. So in other words, more C2H3O2 minus is made in the process. So what they're trying to say in the slide is as the HC2H3O2, the weak acid is reacting with the base, some of it gets used up. So this amount here decreases, but some of the counter ion or some of the conjugate base is made. Okay, so we're told if the amount of sodium hydroxide added is less than the amount of acetic acid present, the pH change is small. Make sure you have a lot of weak acid so that all of it doesn't get used up by adding some of the base. Okay, you want to make sure there's weak acid left over. So in that case, the weak acid will work if you have less amount of base added. And then the other scenario, if a strong acid is added, so now we're focusing on a strong acid. The strong acid can only be neutralized by a conjugate base, not another acid. If a strong acid is added, the added acid is neutralized by the conjugate base component. This time, this is the one that's reacting. This is how they show you how the story plays out. This is the threat that was added, the intrusion, strong acid. Here's the conjugate base reacting with it to form this and that. So the Chatelier's principle plays in the process, right? You have two components reacting, either weak acid or a conjugate base, depending on what the added chemical is. If the amount of ACl is less than the amount of the conjugate base present, the pH change is small. So what they're trying to communicate here is there is a limit to the buffer working. So I'm going to paraphrase what they wrote. As long as the added acid or base is less than the weak acid or base or conjugate base, the buffer will work. Remember in the beginning we said make sure you have enough of the weak acid, make sure you have enough of the conjugate base. You don't want these to run out. Once they run out chemically and the equilibrium is not making any more of them, you don't have a buffer anymore. So if you happen to be reading your textbook, there's a story in the beginning. I think it's in the beginning. They used to have the story of either the dog lapping on antifreeze or the blood buffer. I don't know which one is where, but because they have different editions. Anyway, at some point there's a story about dogs like to lick antifreeze when it pours from cars. The antifreeze messes up with the bicarbonate acid buffer. And if you have enough antifreeze, antifreeze becomes that threat. It can actually mess up the buffer to the point where the dog dies. So the goal is you don't want to run out of the weak acid or conjugate base. Because somebody asked me this one time, if the buffer system can keep itself going by remaking the reactants of the products to keep itself going, can you quote unquote kill the buffer? I said, yeah, you can kill the buffer by adding so much acid or so much base that you use up all of the weak acid available or all of the conjugated base available. The equilibrium tries to replenish it, but then in the end, you just kill the equilibrium. If you kill the equilibrium, you kill the buffer and the buffer stops working. And if it was a life sustaining buffer, you just kill the individual, right? I've watched movies. No, 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 like murder mystery movies. I like murder mystery movies, like Who Done It. Sciency stuff. It's intriguing. Okay, so we're still talking about making the buffer, right? And I talked to you about having chemicals in the container. So this is where I'm going back to where we added the acid first. So trying to show you something called the common ion effect. Okay. And technically, the common ion effect is an effect that happens to the equilibrium. It shifts the equilibrium one way or the other. Okay. So the common ion effect is related to Le Chatelier's principle. And this is that principle of how we can shift the equilibrium to the right or to the left based on certain things that we do to mess up the equilibrium. So let's go back to the part of the story where I was saying we are making a buffer. So this container here shows us making a buffer. We're in the lab, and what we have here is an acid only. How do I know that we have an acid only? Because of this label right here. If all we have in a container is the acid, and we have 0.100 molar of the acid. This is a weak acid, acetic acid. The pH of a weak acid is 2.90. I also recognize the pH because remember, acids have a pH that's less than 7. So yeah, 2.90, definitely acid, and it's a weak acid. Okay. So this is the pH of the acid by itself. And then here we have the pH of the conjugate base before you mix them up, right? You bought in the store, so it has sodium in it, but remember our focus is this part here, the pH of the conjugate base. The conjugate base, because it's basic, its pH is bigger than 7. So for a base pH, we expect it to be larger than 7, 8.90. And then we mix it to make a buffer, right? Because remember, when you take the weak acid and add its conjugate base, you're essentially making a buffer. So we have mixed these two, and then we got the buffer, 4.7, right? So here's the question that they're trying to ask. How do we get 4.7? Don't jump to math, right? Because I'm going to tell you what I'm thinking, right? Me as a student, I know myself as a student. Well, you take 2.90, right? And then you add 8.90, then divide by 2, and you get 4.7. No, that's math. And you would think that's what happens, but no, it's actually even, yeah, it's more about Le Chatelier's principle. So they show you here how it actually works out. We're going to be working out step by step. Okay. We're actually going to get this to work out step by step. But let me go ahead and explain to you conceptually what happens here. why the buffer decreases, because that will help us why from going from here and here you have a low pH, a high pH, why we end up with something somewhat intermediate. Okay, so I'm going to once again write the equilibrium reaction of the weak acid, HC2H3O2 plus H2O. I know I'm writing this a lot. We did it in the last chapter a lot too. We're doing it a lot here. I'll put the H3O plus first. Doesn't really matter which one you write first. As a student, I wrote H3O plus first because it reminded me it's an acidic buffer. C2H3O2 minus. The products are both aqueous. This is liquid. This is aqueous. Okay, so in this container here where we have a pH that's low, the pH is based on the concentration or the amount of the H3O plus, right? So in the last chapter, you learned to figure out the number pH, you take the negative log of this concentration here, the concentration of H3O plus. Okay, so if the pH is 2.9, is that what this is? Then 2.9 relates to the concentration of H3O plus, right? This 2.9 was calculated by knowing the log of H3O plus. Okay, so when you take the weak acid and you add the conjugate base to it, please notice the conjugate base here, we're going to work it out mathematically. Base here is essentially sodium acetate. This part is not important. Adding C2H3O2 minus. What is this doing to the equilibrium? In adding the conjugate base, we're doing the same thing as increasing the concentration of our product. Okay, adding the conjugate base to make the buffer is equivalent, is the same thing as including this concentration, because the conjugate base has an ion that matches this ion here. So it is literally the same, right? So when we add it, initially it only increases this. But they said common ion effect, right? So what we are adding has an ion that's common to the equilibrium. So what happens as a result? The equilibrium shifts to the left because there's too much product. But when it shifts to the left, it has to use up some of the H3O plus to shift left. So after adding C2H3O2 minus, equilibrium, oh, I'm not writing straight, shifts left, the amount of H3O plus decreases. Okay, so when it's shifting left, it just means that the extra amount of C2H3O2, the acid ion that got added, will react with the amount of H3O plus we have present, hydronium ion, to shift the reaction left. We have more of this as a result. We have more of this, but we have less of this. Okay, so by adding more of this, we have less of this, more of this, more of this. But pH is based only on this ion here. So since we have less H3O plus, when you try to figure out the new pH, the number in here is less, and we end up with a pH of, was it 4.7? Yeah, 4.7. So the pH ended up being 4.7. So this is going to be less acidic. Okay, so we're going to work this out mathematically so you can see what I'm saying besides just the conceptual part. I will show you once again how we go from a pH of pH of 2.9, a lower pH, as in a more acidic solution, to a pH of 4.7 right here. So here they work it out mathematically. We're actually calculating the pH of the buffer once the buffer gets made. We're starting out with the scenario we just saw. Calculate the pH of the buffer solution. We know the answer already, right? We're trying to work it out. That is 0.100 molar of the weak acid and 0.100 molar of the conjugate base. Okay, so I know this is written here, but as usual, I'm going to draw my own table. Remember what I showed you before. Even though you're making a buffer, always start with the equilibrium of either the weak acid or the weak base. So I'm going to start here with the weak acid equilibrium, since the weak portion is the acid, right? So I'm going to write the equilibrium form of this acid, just like I just did. HC2, H3O2, AQ, like we did before, plus water, liquid. Equilibrium arrows to give you H3O plus AQ plus C2H3O2 minus AQ. Okay, so this is what we have. Okay, so what they're showing you here is, let's see. Let me start with my table. You're going to have initial, you're going to have change, you're going to have equilibrium amounts. So they start off in this question here, giving you concentrations of the acid, the weak acid, but they also gave you the concentration of the conjugate base that gets added to the solution, right? So if you were doing a regular problem where you're trying to solve for the pH of a regular acid, you would just write the concentration given to you here as 0.100. So you put the initial amount here as 0.100 m, right? We leave this out because remember, equilibriums do not have liquids, so you leave that out completely. And if it was a regular acid problem, because you haven't made any products yet, you put 0 here and you put 0 here, right? Like they're kind of showing you in this first slide. But if you look at this slide down here, they put a number right here. So what's happening here? Because the buffer requires a conjugate base from the beginning, we are going to change this number here and add the conjugate base concentration. So we're going to write this number because this conjugate base has to be present from the beginning. So you're going to write 0.100 molar where the acetate ion is. You put 0.100 molar. And this is how you can tell this is a buffer question, not just a weak acid question. In a weak acid question, you only have a concentration here. Both these products here are 0. In a buffer problem, you need the concentration of the conjugate base, in this case, from the beginning. Everything else continues like we normally do. You will write change in terms of x, right, for this part here. Go back to the stoichiometry. In this balanced equation here, our coefficients are 1 and 1 and 1 and 1. Remember, reactants decrease. So for the reactants, you write minus in the change. For products, you put positive, right, in terms of x. So the reactant here, in terms of x, just say x amount reacts. We don't know what it is yet. We'll figure it out. And then over here, for the product, based on the coefficient, X amount gets made, X amount gets made, right? Remember, the coefficient here is 1 and 1 and 1, but instead of writing the number 1 and 1 and 1, we're writing X because we don't really know what the actual amount is. We're writing relative amounts, okay? So if it's 1 and 1 and 1, then we say, what if X amount reacts here? Then X has to be produced here, X has to be produced here. Okay, for equilibrium, take the initial, add change. Okay, so it's going to be 0.100 minus x, 0.100 plus x. I'm going to leave the units out, okay, because just to keep it less complicated. Okay, equilibrium amounts are always initial plus change, initial plus change. So I think I got that. Okay, just like what we did before, we are going to be trying to figure out the value of the value of x to solve for x. Okay, here's the thing. There is a number we need that was not given to us in the beginning of the relationship. Remember when we're solving for x before we did the equilibrium expression, we brought in the Ka value. They didn't give us a Ka value. We need the Ka value. I'm assuming they bring it in later. Yeah, all the way down here. Bruh. Okay. It would have been nice had they brought it up in the beginning. We need a Ka value. Remember, this equilibrium equation goes with this Ka value, 1.8 times 10 power negative 5. That helps us to solve for x. So over here, to solve for x, I will use equilibrium expression. Okay? So let me write the expression here. Ka, equilibrium expression, is equal to the product concentration, H3O times C2H3O2 minus divided by HC2H3O2. And remember, since this is K, all the numbers in here have to be equilibrium numbers, meaning that I can only put in these numbers in my K expression. I cannot put initial ones. To put initial ones, I have to use Q, right? So I know what Ka is. I can bring that in here. Ka is 1.8. Ooh, this point 8 is horrible looking. 1.8 times 10 power negative 5. That's Ka. That Ka always goes with the acetic acid equilibrium. What's my value of H3O plus at equilibrium? This is X. X times this one here. 0.100 plus X divided by this number here. 0.100 minus X, right? Okay, now I take a moment to pause and I'm like, this sounds like difficult math. Yeah. So I'm like, is there a way out of this mess? 5% rule. Let's check the 5% rule. Can the 5% rule exonerate us from this great math? The 5% rule, remember? So we're going to apply that. Allows us to, if possible, avoid the quadratic equation because this format right here that I see right here is giving me quadratic equation vibes, right? So I'm like, I'm trying to see if I can avoid that. 5% rule. Take your Ka value divided by the initial concentration of any of the numbers you have. I'll just say my initial concentration of my acid, Ha for my acid, times 100. Do I get 5% or less? Let me see. Ka, 1.8 times 10 power negative 5 divided by 0.100 times 100. And I have my calculator here. 1.8 exponent negative 5. Oops. It will help if my calculator is on, y'all. 1.8 exponent negative 5 to the right, close parentheses, divided by 0.100 times 100. Okay, I get 0.018, whatever, passes. Passes. So what does this allow me to do? It only allows me to knock off this plus x and this minus x. Only the x's that are being added to non-x numbers. I can't knock off that one. So it allows me to simplify my number to 1.8 times 10 power negative 5. That one doesn't change. X remains as x. In here, I can make this becomes 0. That becomes 0. This becomes 0.100 over 0.100. Because it would be like 0.100 plus 0, 0.100 minus 0. So this is what my number becomes. So much easier. You can tell I'm smiling, right? So much easier. So now I solve for x. This and this cancels out. And x is literally 1.8 times 10 power negative 5. Okay, what were we doing again? Solving for pH, right? Once we have our x value, now we want to go back and plug it into the ice table because they said solve for pH. Okay, So I have to go back here and erase this. Erase that. Erase all of this. I feel like it's layers. So here I put minus 1.8 times 10 power negative 5 plus 1.8 times 10 power negative 5. Now that I know what x is, I can plug it back in here, right? 1.8 times 10 power negative 5. So I'm going to do my actual math. 0.100 minus 1.8 exponent negative 5. Okay, here I get 0.09998, which you can approximate to 0.100. Okay, this is why it's okay for us to round off. And then here, same thing. Well, I guess you're adding, so it's kind of different. Here's it's going to be 1.8 times 10 power negative 5, right? Because it's 0 plus this number. The last one here on the right, 0.1 plus 1.8 exponent negative 5 equal, oops, 0.10018. Once again, this is too many decimal places. When you round this up, you end up with 0.100. Okay, this shows you why it's okay for us to round off those numbers. Anyway, now that I have my H3O plus value at equilibrium, right, I'm going to continue with that. So H3O plus at equilibrium is equal to 1.8 times 10 power negative 5 molar. Now I can figure out pH at equilibrium. pH of the buffer solution at equilibrium is, drum roll, pH is equal to, I know it's not as exciting, like I don't know what you're thinking about, but it's like this is like the finale, right? Negative log base 10, 1.8 times 10 power negative 5. And so I know it's not as simple as averaging it out, right? So let's see, where's my log 10? I have to find my second log to the back. Okay, so I got log 1.8 exponent negative 5 to the right, close parentheses. Okay, so yeah, when I work this out, I get negative, yeah, when I put a negative there, I get 4.744, which approximates into 4.74. Okay, so if you are working in a company, some people, you know how we buy solutions, pre-made solutions? Some people, their whole job is to make buffers. Well, not just buffers, but a bunch of solutions, right? So you have to have that skill of not only mixing the chemicals in the lab, but figuring out what the pH of the final solution is. So you will have a notebook and you be writing all this math. Because when you work in a company, you have to keep a notebook. Yeah, you have to keep a notebook, and the manager comes to check it. Yeah, whenever the company is being audited, they'll come and check the notebook of the scientist. I remember working for a company like that. I wrote on a post-it, and somebody told me I could get fired for writing my notes on a post-it. You're not supposed to do that because your work has to be audited. They have to be able to audit your work, so there has to be a notebook. Huh? Yeah. So all this stuff, they did the percent rule, they worked it out, there it is. Okay, so that shows you the ice table. Now I'm gonna show you how we get to the same answer, okay? By an alternative method. We normally don't have a lot of alternatives in chemistry. A lot of people will ask me, is there an easier way? I'm like, listen, if there was an easier way, I'll teach you that one first, okay? But this time we have an alternative, but there's a caveat. Caveat. You can only use this in the context of making a buffer. If the question is asking you figure out the pH of a buffer solution, you can only use this equation. And so here's the thing. This equation is only meaningful to you if the 5% rule has passed. So you're told here To use the Henderson-Hasselbalch equation, HH equation, H squared equation, you have to verify that the Ka divided by the acid concentration is less than 5%. If the 5% rule has not passed, you cannot use this. You have to use the ice table and go through the quadratic equation. Okay? If you didn't like what I just did with the ice table, then you have an alternative. For the first time, I introduced to you Henderson-Hasselbalch equation. This is used for calculating the buffer pH. Okay, if you take junior level biochemistry class and you make a lot of buffers for living systems and stuff, it is your role as a scientist slash student to figure out the buffer of the actual solution made versus what you thought you made. Okay, and you will verify this with equipment. But anyway, so here it is. This is the formula for finding the pH. So this reminds me of back in the days when I was in school. By junior level, y'all, I wasn't sure what this formula was for. I laugh at myself now because I'm like, we were learning things at content that was so fast. There was no PowerPoint, there was not just a textbook and a teacher right on the board. So we were struggling to keep up, to keep our head above water. Right. So I didn't really know what this was for. I just kind of guessed when I was using it. Okay. And then I will kind of switch these around. So I'm telling you, purpose of this equation is to find pH. Okay. So the pH is the part that's by itself on the left of the equation. I was switching them out because, to be honest, the textbook I was using was switching these around, and that was confusing me because I didn't really understand what I was doing. So I didn't understand the relevance of it. Learn it in this form. Okay, makes it easier. You're usually trying to find the pH. If you're trying to find the pKa, you can always rearrange the equation. Okay, pH. You can find the pKa. This part is technically in parentheses like that. Okay, so let me go ahead and add a page so I can write more freely. It's pH that you're solving for. Remember, pH came from pH equal negative log base 10 of the H3O plus concentration. Okay, so I'm going to actually just write it like this. Is equal to pKa. I hope in the other video I told you that I noticed at some point, because the teacher wasn't making these connections, that P in this chapter here stands for negative log base 10 of whatever. So this is negative log base 10 of Ka plus log base over acid, like that. Okay? Yeah. And so the base will usually be the conjugate base in the balanced equation, the equilibrium equation. Then the acid will be the weak acid. So find your weak acid. Here, these are the concentrations. The conjugate base concentration, weak acid concentration. You plug them in here, divide them, get log, and the, negative log base 10 of the Ka, negative log base 10 of the H3O plus. Plug them in here and solve for whatever they need. Okay? Remember, you can only use this if the 5% rule passes. Okay. Do they have us use this to figure out the 5? Okay. We're going to be using Henderson-Hasselbalch HH equation to calculate the pH of a buffer. Okay. So what I'm going to do here is I won't go through this one here. They show you this method and they show you the other method. I'm going to go through the Henderson-Hasselbalch version straight away. Okay. So yeah. Oh, I see this because I'm like, why is it kind of skipping around? Yeah, I'm gonna start with the Henderson-Hasselbalch equation straight away. So let me start with that first because I'm trying to show you that this is a new part. Calculate the pH of a buffer solution that is 0.050 benzoic acid. They gave you this formula here. So you want to write your equilibrium for the acid first. Remember, if you have the weak acid, write the equilibrium for the acid first, then you put the other information. So benzoic acid has this formula. Its equilibrium is going to be HC7 Oh, H5O2 aqueous. You always add the water. The water is always liquid state. You have your equilibrium arrows. You have H3O plus aqueous. And then write the formula minus the H. And then, so skip the H, C7H5O2 minus. Because remember, this formula here, which is now a conjugate base, lost an H and a positive. Okay, so I'm going to read the rest of the question. It says, okay, calculate the pH of the buffer solution that is 0.050. So the amount here of this, right, benzoic acid, is 0.050 of the weak acid and 0.150 of sodium benzoate. I recognize this as the conjugate base. So this number here is 0.150 molar. And then they gave me the Ka for the equation I just wrote to be 6.5 times 10 power negative 5. Okay, since I'm illustrating the Ka, the HH equation, I'm just going to write this down here. To get my pH, I need pKa plus log of base over acid. Now remember, the base here is conjugate base. The acid here is weak acid. So let me see what I have. This is my weak acid. This is my conjugate base. So I have this number and I have this number. Oh, and I have the Ka. Okay. So I'm going to actually start by solving this. I'll do this number 1 first. To find my pKa, I'll just make it negative log base 10 of the Ka's. Ka is 6.5 times 10 power negative 5. Okay. Make sure you put this in parentheses so you get your answer right. Where is it? On button. Why do you go to sleep, calculator? Negative second log. I should invest in a more expensive calculator. No, I'll struggle through. The struggle is good for my brain. Negative log base 10, open parentheses, 6.5, exponent negative 5, close parentheses. Let's see. Oh, I got it. 4.187. I'll use all those numbers. So I'm done with this part. Done with this part. Next, I'm going to do this part here, right? So I'm doing this step by step. I'm going to do the log of base over acids. I'm going to write this shorthanded here so I can see. Okay, I need a log, but in parentheses, what's my base concentration? Oh, right here. 0.150 molar. Then my acid concentration, 0.050 molar. Okay, so I'm going to put a log, second log, 1, okay, log, 0.150 divided by 0.05, close parentheses. Okay, so here I get 0.477, okay? So now I plug these back into the formula. I got all of this part worked out, right? So pH is going to be equal to 4.187 plus 0.477. So I take the second answer, I add it to my first answer, and I get pH equal 4.66. Okay? So much simpler, huh? I mean, it really depends. But remember, chemistry is a problem-solving class. So it's not about knowing how to solve things one way. The strength in chemistry is knowing how to solve the same problem different ways. That's usually the ultimate goal. So it's not about just knowing how to do it one way, right? So you want to know how to do it this way. Because when I was a student, I'm like, I'm going to pick the best way and I'm going to go with that one. But as I got into junior level in grad school, I realized the goal was to know it all the different ways versus knowing it one way. But in the beginning, man, my goal was survival. I was like, no, I need to survive this class. But when it became my major, I had to kind of grow up, right? So yeah, Henderson Hasselbalch gives you this. And so they go ahead and let me show you. Yeah, they work it out here too. They get the same answer. In more one fell swoop, or I guess one swoop, they get the answer. But then they also work it out here, which the order of the slides don't look right to me, but they do it the regular way where you have your equilibrium here, you put your initial for your acid. Oh, they skip the water. Oh, and then you have your two products here, this amount here. You have your change in terms of x, the coefficient 1 to 1 to 1 to 1. Change in terms of x. You add these two, use the Ka they give you. So I think this continues down here from what I saw. Use the Ka expression. Oh, apply the 5% rule. Decide that the rule passes, yay, because you see how they round off this part and round off that part to simplify here. Solve for x, and then once you have the value of x, take the negative log of that and you get 4.66. So either method should work. Okay, I didn't want to work that out step by step because it takes a longer time to do that. This is just showing you what I showed you guys before, how the buffer works. I've talked about this before, but I just want to talk about it again since they bring it up here, that there are some changes in the buffer as you add the incoming base, because you want to know how to answer questions like this in the quiz, in the homework, and possibly on the exam, right? What happens to the pH of the solution when you add an acid or a base to the buffer solution? So they try to enact it here. Okay. Yeah, they try to enact it here conceptually. Okay. So let's assume this part here is the beginning. Okay, the middle is the beginning. This is a picture way for them to show you what is happening. Okay, in the beginning, you assume you have equal concentrations of the weak acid and the conjugate base. Okay, so this is a weak acid equilibrium, right? A weak acid buffer. So you have same amount of the weak acid and same amount of the conjugate base. Since they use HA here, let me go ahead and write equilibrium expression, or sorry, the equation real quick over here, just so you can have a visual, an additional visual plus H3O plus. So we're talking about this. We're focusing on the amount of this and this. In the beginning, these amounts are equal. Okay, then what happens? The incoming thread is an acid. Remember, if the incoming thread is an acid, the component of the buffer that must react to neutralize the acid is A minus. This is a base, right? So if the acid comes in, the base has to be used up to neutralize the acid. So what happens? How do we know? They show the equal concentration here by these pictures. So these are the particulate level, right? Imagine you have equal amounts of acids and base. This is an acid, 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 acid. So this is acid, 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 which they show us HA, 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 HA. Since the acid comes in, a quick assessment is done by the chemical and decides only the base can neutralize the acid. According to what we have here, it looks like the amount of acid that got added was just 1. How do I know that? Because the amount of base that got used to neutralize the acid is 1. There's only one circle missing here. Y'all see that? We went from this to this. So the base got used to neutralize the acid. In the process, more HA was made. So you can see the changes here, right? More HA was made. Now we have a little less HA. We have a new equilibrium, but the concentrations of the acid and the base required to make the equilibrium are different from what we started off with. Okay? Over here, what if the thread or the incoming thread this time, or the disturbance, is a base, not an acid? So we start off once again with equal amounts, and this time a base gets added. When a base gets added, what do we see? We go from this one being the chemical required to neutralize the base. The acid has to neutralize the incoming base. How do I know it's base? Remember, OH signifies base, H plus signifies acid. So you can see one of the acid gets reacted with the base to neutralize the base. In the process, it makes extra A minus. Okay? According to this picture, But how do you use the equilibrium to come up with that? So we're seeing here, if an acid, wait, I think they show it down here. Yeah, yeah. If the acid is added, once again, remember the conjugate base has to react with the acid. Okay? If the base is added, if the base is added, the weak acid has to react with the base that's added. So for right now, let me leave it like this. I usually go over board in the beginning. I want to wait until we get to that part before I go into all those details. For right now, let me go ahead and skip straight to this part here and talk about how we can then figure out the pH after we have had the disturbance. So here we're using the buffer, right? And the buffer is used. So after the buffer has responded by reacting with acid or base. So we have used the buffer. The buffer worked. But what is it when we say the pH didn't change? Did it really not change or did it change slightly? We can use a modified version of the Henderson-Hasselbalch equation. So you're seeing here is a modified Henderson-Hasselbalch. I just call them HH equation. It still helps us get the pH, but it helps us get a pH of after neutralization has happened, after the enemy has been neutral. What am I writing? Neutralization. I just wrote nutration. My goodness. After neutralization. So we have already neutralized, in this case, the strong acid. What is our new pH? After we have neutralized the strong base, what is our new pH? So we are figuring out the pH again, but this time it's after neutralization. So what I'm going to say here is to kind of just cut to the chase. The effect of adding strong acid, actually the strong acid concentration ends up increasing the acid amount, but in the process decreases the base amount. Okay? And this is what I was trying to show you back here. When you add the acid uses up the base in the process and then makes more of HA. So in a way, it kind of shifts the equilibrium so that more HA is made in the process. It's a weird reaction, but that's how it works out. When you add the acid, it makes more HA in the process. So it actually ends up increasing the acid concentration, but uses up some of the base. So this goes better with the picture, right? Like I showed you guys back here. The base does the opposite. When the base comes in, remember some of the acid has to be used to neutralize the additional base. In the process, extra base is made. So this is the effect. This is how it plays out. We end up with less acid, but we end up with more base. Here we end up with more acid, we end up with less base. Anyway, long story short, apply to the formula here and you can figure out the pH after neutralization. So what I'm going to do is I'm going to cover this part here, this last part, and then we're gonna end. Yeah, I'll say we'll end here for today and pick up here for next week. Okay. So for this part here, I'm actually gonna use the Henderson-Hasselbalch equation. We're told calculating the pH change in a buffer solution after the addition of a small amount of strong acid or base. Once again, make sure you know this. So we're told a 1 liter buffer solution contains 0.100 molar of this weak acid and 0.100 molar of the base. Okay, before I continue, I usually feel a lot more comfortable writing the equation. It helps to anchor all the dialogue. So I'm going to write the equation of the weak acid, HC2H3O2 AQ plus water, my equilibrium arrows, H3O plus positive, oops, positive AQ plus C2H3O2 minus AQ. Okay, and I remember the Ka that goes with this equation is Ka equal 1.8 times 10 power negative 5. Can I make this smaller? It's hard for me to write smaller initially, but let me see if I can make this smaller. Oh, okay. I don't like to write the number up there. So it's going to be negative. Ka is 1.8 times 10 to the negative 5 for this equation. Okay. So they were saying a 1 liter buffer contains 0.1 molar. Okay. So the concentration of this one here is 0.100 mol in the volume of 1.00 liters. Remember the numbers written down here are usually big M, not moles per liter. So I'm just going to take my moles per liter to get my big M, molarity. Just divide these two numbers and I get 0.100 big M. So I have used this number and used that number. And 0.100 mol of the base, the conjugate base, this one here, same thing, 0.100 mol in 1 liter is the same thing as you just divide these two numbers and you get 0.100 big M. So I'm going to write that down here, 0.100 big M, because the numbers that we normally use in the table are in the units of big M. So I'm right here now. The value of Ka for this is 1.8 times 10 power negative 5. Oh, I already have that, so I'm right here. Because the initial amounts of the acid and conjugate base are equal, yeah, they're equal. The pH of the buffer is equal to pKa negative log 1.8 times 10 power negative 5 equal 4.78. Ooh, I feel like they're kind of rushing for me. So I am going to do this my way. Let me figure out the pH of the buffer. And I told you guys I will use Henderson-Hasselbalch. So I'll say using H equation. So pH equal pKa, no shorthands, no shortcut, log base over acid, right? pKa is negative log base 10 of Ka. Ka is this number right here, 1.8 times 10 power negative 5 plus log of, what's my base? Oh, base 0.100 molar, acid 0.100 molar. I'm showing you how to not be threatened by big questions. I used to be that person who, I told you I'm not, words aren't my strong suit. So when I see words, I'm like, oh, there's so many of them. It's part of my history, part of my journey. It is what it is. There's so many of them. Couldn't they say this in fewer words? Yeah, but now I'm like, oh, just break it down. Look at it a little at a time. Okay, let me solve this part right here. So I'll take my calculator, which is now back to sleeping. Negative second log. No, I'm just trying to find my log, okay? Parentheses, 1.8 exponent negative 5 to the right, close parentheses. Here I get 4.74, okay? Plus, this divided by that is 1. So what is log of 1? So, let me get my log function. Oops, that's not the right thing. Log, okay. Log of 1, 0, 0. So 4.74. So I got my pH of my buffer, right? And I got it as 4.74. So let me see what they were saying, because I think that's what they were trying to say. They were saying because the initial amounts of the acid and the conjugate base are equal. Oh, they were saying because these two numbers are equal, when you divide them, you end up with 1, and log of 1 is 0. Okay? That's what they were saying. Okay? The pH of the buffer is equal to pKa, like I just did, negative log of this is a Ka, and that will give us 4.74. Okay, I just confirmed what they were saying. Now they're saying calculate the new pH after adding 0.01 moles of solid sodium hydroxide to the buffer. Okay, here's the key. Even though you're adding solid, when the solid gets into solution, it will become aqueous. So don't get so, I mean, if you're a person to get caught up with words, you're okay. When the sodium hydroxide solid gets added, it will become sodium hydroxide aqueous. So you're fine. So we're not going to be dealing with this anymore. So you shouldn't say nothing will happen because we're going to be dealing with the aqueous sodium hydroxide. Long story short, all they're trying to say, you're adding a base. And how much base are we adding? 0.01 molar. Okay. So add 0.01 molar sodium hydroxide, which was a solid, but it will become aqueous solution, 0.01 molar, right, to 1 liter, yeah, to the buffer. Okay, so since I'm adding this, they want to know the pH after. I have to use the modified Henderson-Hasselbalch equation, which says pH is pKa plus. Since I'm adding base, the one that I'll have less of is the weak acid, right? So, oops, I skipped over the log part. The log of conjugate base over weak acid. So the weak acid will be decreased to because of the base being added, right? So this is going to be a strong base right here. And then somehow in the process of the weak acid decreasing the base, it will create more of base in the overall solution. So this is the equation I'm going to be using, the modified Henderson-Hasselbalch. Okay. Okay. So now I'm ready. Let's see. I do have my pKa, but I'm not going to use a shortcut. I'll just say pH equal negative log base 10. Since the original acid is the same, it hasn't changed. What was the number again? Oh, 1.8 times 10 power 5, negative 5, my bad, plus log, what is my original concentration? Wasn't it like zero point 0.1? Yeah, it was 0.1.1. The top number was 0.100. The bottom number was 0.100, right? But now we have to subtract for the bottom number 0.01. And the top number, you have to add 0.01. And that's the only thing that really changes here. Everything else remains the same. So since this that I did before produced this number, I'm not going to do the math again. It's still 4.74, right? This is the part that changes. So I'm just going to add the numbers to make it easier for myself. 0.100 plus 0.01. I'm going to do the math slowly, y'all. 0.11 molar over 0.100 minus 0.01, 0.09 molar. Okay. Now, 0.11 divided by 0.09 gives us log of 1.2. I think your lab this week is something like this. The lab that goes with this part here. So take the log of this answer and you get, I have to look over the lab again, 4.74. So when you add this to 4.74, I get 4.82. Okay. Okay. So I'm about to conclude what I just did. The pH of buffer before neutralizing base is 4.74. pH of buffer after neutralizing base is 4.82. I'm going to be controversial here and say, how is this maintaining the pH? maintaining slash keeping constant pH of solution. In other words, okay, 4.74 is not equal to 4.82. I'm going to be controversial like that. How is this keeping constant? Okay, so it's kind of like they knew I was going to ask this question. Okay, I've taught this class before, so I know what's coming up, right? But when I was a student, I was the kind of person, when I was really in tune with the subject area, I would ask these questions and my teacher would give me this look like, when are you graduating? I'm like, I'm not trying to challenge you or the author. You're just saying stuff that is not clicking in my head. You said constant, but the pH changed, right? So it's like they knew I was going to say that. They said, okay, for comparison, okay, calculate the pH after adding zero point 0.1 mole, the same amount of base, to 1 liter of pure water. Okay, what am I trying to compare? Let me paraphrase this. What they're trying to say is, if you think that wasn't maintaining pH, let me tell you what the same amount of base would do to pure water, because pure water does not have buffering capacity. Okay, pure water is just water, H2O. It doesn't have a buffer in there. So if you think that the buffer is not good enough for your standards, let me show you what would happen to the solution if the buffer wasn't working. I'm not going to work that part out because this is kind of like, trying to put you in your place kind of question. To make you understand the value of the buffer, I'm just going to show you how they work it out. So here's where they work it out. So if you had 1 liter of water with no buffering capacity, okay, and then you added the same amount of base you added to the buffer, the water will go from pH, that's 7 because it's water, it's neutral, to a pH that is 12. That's how many points? A 5 point increase. Over here, what was the change? It wasn't that much. We went from 4.74 to 4.83, and then you were still complaining. This is me. I'm talking to myself, right? I was the one who was like, what? Okay, so 4.83 and then 4.74. Yeah, the only increase we saw here was like a 0.087. So in the world of chemistry, the buffer is working, because without the buffer, we would have had a 5 point increase. Without the buffer, it would have gone from 4.74, 4.74 plus 5. It would have gone from 4.74 to 9.74. So they're just saying the buffer is not perfect, but the buffer is still doing its job. It is still maintaining the pH, so that the change is very, very small. It is considered insignificant. Okay, so here on, we move on with humility. We have learned the buffer does work, right? It works to maintain the pH, because if it wasn't working, we would have a 5 point increase when we added that amount to the solution. Anyway, I'm going to stop here. It's just too much drama. No, I've been talking too much. Okay, but yeah, so this is what they're saying, that yeah, recognize the buffer works. The buffer did help the solution remain very close to what it was before. Without the buffer, you would have had about a 5 point increase in the pH, and then you will be complaining. And so for people who do research in biology and where they have to maintain a human pH, a blood pH or something, they will use a buffer. And if you're doing the research and you forget to use the buffer, and there is a change like this, it will mess up your whole experiment, because now you'll be doing the experiment in a whole different environment. So buffers are important, and making them right is important, and making sure you have the right amount of the buffer, the components of the buffer is very important to make sure it works, number one, it works for a long time, number two, and is able to work effectively. Okay. Anyway, this is where I'm going to end today. Any questions?
No, thank you.
Okay, you're welcome. Talk to you later. Have a nice weekend.
You too.
Okay, bye. Where is the stop? Stop.